Hello and welcome back to another video of Total Organic Chemistry. This video we're going to be taking a look at the second half of my discussion on radical halogenation. This time we're going to be looking at a little bit of the issues with selectivity in this reaction. So last video we were working with just methane, CH4, but what if we perform the same reaction on a molecule with more than one type of hydrogen? So maybe propane, which is 3 carbons. We can also draw it like that with the bond line structure. And if we halogenate this with chlorine and ultraviolet light, we'll get 2 different products this time. So one of our products will be where the terminal hydrogen is replaced with chlorine. So we end up with CH2Cl on the end. And remember that these 2 carbons are identical. So adding the chlorine here would be the exact same as adding the chlorine here. It would just be flipping the molecule around, looking at it from a different perspective. So we can add it on the end, or we also could add it into the middle carbon here, like this. And then we can also draw these molecules like so. So which of these products would we expect to get, or would we expect to get a mixture? Well, if we look at just the statistical probability of chlorinating each position, we have 6 carbons on the end, so we have 6 hydrogens, so we have 3 here. Let's do it over here. So we have 3 carbons. Wow, I am just retarded. So which of these products would we expect to get, or would we expect to get a mixture? Well, we can look at it statistically with just the number of hydrogens at each position. So we have 3 hydrogens at this position and 3 on this carbon. So we could imagine if we have 8 hydrogens total, so we have, remember, 2 at this middle position here, we could imagine that we would get 6 out of 8, or 75% of this product, and then maybe 2 out of 8, or 25% of this other product. But what's interesting is that we actually see a different ratio experimentally. So experimentally, we might see something closer to 43% of this primary product, and the remaining 57% of the secondary product. So let me clarify, this is statistically just looking at the number of hydrogens at each position, and these other numbers will be the experimental values. And why would that be? Well, if you've looked at my video on the stability of carbon radicals, you might remember that secondary radicals are much more stable than primary ones. So the secondary radical, the middle position in our propane molecule, is going to be a lot more stable than the end positions, which are primary. Because remember, this is radical halogenation, so during the propagation step we'll be forming either a primary or a secondary radical in this process. And we can figure out how reactive the different positions are by doing just a little bit of math. So usually there's not much math in organic chemistry, but bear with me for a few minutes. So let's say let's take this 57% for the secondary product and divide that by the number of hydrogens that could be removed in order to get that product. So we have 2 hydrogens at that secondary carbon. Then we can divide this whole thing by the 43% that we observe for the primary product, divided by the 6 carbons that are, the 6 hydrogens that are available. And what we end up getting is something right around 4. So what this tells us is that the secondary radical, at least for the chlorination, so using chlorine as our halogen, that chlorine is 4 times more likely to attack the secondary position than it is to attack the primary position. That's what gives us this difference in the ratios of products that we obtain versus what we would just expect from the number of hydrogens on each carbon. So what if we take another molecule that has another type of carbon? So we can take this compound, 2-methylpropane, and let's do the same sort of reaction. Chlorine and ultraviolet light. And what 2 products will that give us? Well, we could have the chlorine attack the primary position here to form this compound. And we could also have it attack the tertiary position to form this compound. And again, we could look at the statistics. We have 9 hydrogens total that are primary. Let's use the red again for primary. Primary position, and primary. And that'll give us 9 out of 10, which is 90% this product. And then let's use blue for the tertiary. And only 1 hydrogen is at that tertiary carbon. So in theory, that would give us 10% of the tertiary product. And I will again specify this is statistically. So what if we look at the experimental statistics, or excuse me, the experimental values again? So this turns out to be 64% of the primary product and 36% the tertiary. Again, we have another discrepancy between just the number of hydrogens and what we actually notice when we perform the reaction. So, if you can imagine, this tertiary radical that we form when we're producing the second product is again going to be even more stable than the secondary radical, so much more stable than the first, the primary radical. And we can do the same calculation that we just did, where we have our 36 over 1 hydrogen divided by the 64% for the primary, divided by 9 hydrogens possible. And this gives us about 5 times more reactive. So the tertiary radical is going to be 5 times more likely to form when we're using chlorine. And this is what we call selectivity. And selectivity is going to be a very important concept that we will talk about at length throughout all of these chapters and all of these different reactions that we'll look at. Selectivity tells us how likely a reaction is to happen at a certain position in a molecule, or to one molecule over another. There's several types that, again, we will talk about in the future. At a certain position in the molecule, we'll say for now. So let's take the same reaction that we just did with this 2-methyl propane, but instead of reacting with chlorine, let's do fluorine this time. F2 and ultraviolet light. So again, we can form two products. The only thing that's different is the halogen. So we have our primary product there with the fluorine on the end, and then our tertiary product with fluorine there. And we would expect the same statistical ratios, right? We expect 90% and 10% of this one. Experimentally, we actually get different values this time because we've changed the identity of the halogen we're using. So we get 86% and 14% the tertiary. So these aren't that far off of the statistical values, so that might seem a little bit interesting to you. Not nearly as much as the spread that we got for chlorine, which was basically 1/3 and 2/3. So I'll talk about that in a minute. Before we go on, let's just do bromine to balance it all out. Again, same two products. Only difference is the identity of the halogen. And in this case, we actually get only 0.06% of the primary product and a whopping 99.94% of the tertiary one, experimentally. So again, we could do the same math on all of these, and I'll leave that up to you if you'd like to do that, to get a little more practice in. But what I'm going to summarize is the reactivities and the selectivities of these different halogens. So what we end up finding is that if we draw a little table here, we have the fluorine radical, chlorine radical, and the bromine radical. And then we have a couple different types of carbons, or different types of carbon-hydrogen bonds, where we have CH3H, we'll say this is the methyl CH bond, a primary, so with one R group, secondary with two R groups attached, and tertiary with three R groups attached to that carbon. So what we end up seeing is, let's start with chlorine. So we define the primary reactivity just to be 1. It's just arbitrary, it doesn't mean anything physically, it just means that that's what we're basing our measurements off of. So we'll start with 1, and then the values that we calculated earlier are that the secondary position is 4 times as reactive, and the tertiary position is 5 times as reactive. We didn't do the calculation for the methyl, but it turns out to be 0.004. So very, very low. Remember that methyl radicals are very unstable, they really don't like to form, so you won't really see them at all. For fluorine, we have again 1, 0.5 for the methyl radical, 1.2, and 1.4. So this kind of explains what we saw with the experimental values for fluorine. They were pretty close to the statistical values actually, and it shows us that fluorine is actually not very selective. All of its values are pretty much around 1. And then with bromine, we get 0.002. This time the secondary value is 80, so 80 times as reactive as primary positions. And then we get 1700 for tertiary hydrogens. So bromine is very, very selective. It will almost always attack the tertiary positions over primary or secondary ones. And just as a note, these are all values taken at 25°C, so just around room temperature. If you raise the temperature a lot, these values actually become less, so you'll get actually less selectivity at higher temperatures, because remember, at higher temperatures, all your reactions are going, all the collisions between molecules are going to end up in some sort of reaction, so it's a lot harder to control whether, for example, the chlorine attacks the primary or the secondary or the tertiary positions. So this is because if you watched the last video, we talked about how the later transition states in these radical halogenation reactions and later transition states in general are characteristic of very slow or endothermic reactions. And the other consequence of this is that later transition states result in greater selectivity. So remember, we talked about how fluorine has a very early transition state because it is so electronegative, so that HF bond is very strong. And because of that, it's going to pull off every hydrogen in your molecule. And there's not going to be any sort of issue, whether it's primary, secondary, methyl. It's pretty much going to pull them all off the same amount, with slight variations, but not much. But, for example, bromination will be much slower. It'll take a lot longer to happen, and therefore we get higher selectivity. So in this case, we have bromine is the most selective over chlorine over fluorine. And if you're wondering why I haven't talked about iodine at all, it's because we don't really use iodine for these types of reactions. It is so incredibly unreactive that we really have to really heat the reaction up or use some other process in order to get the same thing to happen. So iodine's not really useful at all. And honestly, neither is fluorine. So like I mentioned in the previous video, we mostly care about bromine and chlorine for our purposes. One last thing I want to leave you with is an example of how this discussion on selectivity of radical halogenation might be useful. So if we draw this compound here, it's called methyl cyclopentane. We can see the cyclopentane ring with 5 carbons and then our methyl group coming off of it. And if we subject this to chlorine gas and ultraviolet light, our conditions for radical halogenation, how many different products could we get? Well, we could imagine chlorination happening on the methyl group right here. We could also get chlorination on the tertiary position here, and then we have two different secondary positions. So the secondary carbon adjacent to the methyl, and also the secondary carbon over here. And remember that these two positions, so these two positions are the same, just flipping the molecule around, looking at it from a different perspective again. And so are these two. So if we think about our selectivities that we looked at in the table just now, we can actually calculate what the expected proportions of these products would be if we perform this reaction. So for this first primary product on the methyl group, we know that there are 3 hydrogens, so we can say 3 hydrogens times the selectivity of primary carbons in a chlorination reaction, which if we look at the table was just 1. So this is equal to 3. And we can do the same calculation for these, so we have 1 hydrogen at the tertiary position, and the selectivity is 5 times. So this is equal to 5. For the secondary positions here, we now have 2 secondary carbons at each spot. So we have 4 hydrogens, 2 for each carbon, times the selectivity of a secondary carbon in chlorination, which is again 4. So that gives us 16. And then it'll be the same calculation for these 2 spots. 4 times 4, so 16. And these are our ratios. So if we convert these to percentages, it's just a simple little bit of algebra. We can get 7.5% about of the chlorination happening at the methyl group, 12.5% at the tertiary, and then 40% each for each of the secondary positions. And what this tells us is that this wouldn't be a very useful reaction because both of these secondary positions have such a high percentage, 40%, and they're both equal. So we wouldn't get a very good yield because we would have to throw out more than half of our product. And especially if we were looking for, if we wanted to chlorinate at the primary position here, we would only get a 7.5% yield of that, so we would have to throw away more than 90% of our products. So maybe we could use a more selective reagent, such as bromine, if we wanted to get a very good yield of maybe the tertiary position, or perhaps a mix of the secondary ones. So that's the end of this video and the end of this discussion on radical halogenation. Thank you again for watching Total Organic Chemistry. Please be sure to like and subscribe, and look at my Patreon page, and that really helps us continue to make videos for you and continue to provide content. And I will link that again in the description.